And there we go. All right. So again, welcome back, everyone. Hope you had a pleasant transition into the new year. Let's hope the new year will be better than the last one. Welcome back to the lecture. Let's see what we did last time. Last time we talked about the branching program model of computation, and as you recall, a branching program or a matrix branching program is given by a set of matrices. Let's call them S1, 0, S1, 1, and so forth, S2, 0, S2, 1, and so forth until SL0 and SL1. And each of these columns of this branching program is associated with an index xi. Let's say here we have had x1, or let's say here. Here we have xi1, xi2, and so forth. And if xi1 is, let's say, i1 is equal 0, we're gonna take this matrix here, and xi2 equals 1, then we take that one here. So for each column, we pick one of these two matrices, and then in the end, we just multiply them all together in their prescribed order, right? Matrix multiplication does not commute, so we have to multiply them together in a fixed order. In the end, we either get the identity matrix, which we will interpret as output 0, or a non-identity matrix, which we will interpret as output 1. So this is a fairly simple model of computation, but we have seen via Barrington theorem that branching programs or matrix branching programs of polynomial size can compute so-called NC1 circuits, that is, circuits of logarithmic depth. And maybe as a quick hook back, I have already mentioned that many interesting cryptographic operations like encryption and decryption for many interesting encryption schemes, including the GSW fully homomorphic encryption scheme, can be done in NC1, right? So NC1 is a class which captures mostly parallel computations, or computations which can be performed in parallel but don't take a lot of time. They are not very deep. Okay, so that's a quick recap what we did last time. And a natural question one might ask oneself is, are branching programs maybe already a form of obfuscation, or is Barrington theorem sort of a kind of obfuscator? Does it make branching programs NC1 circuits, does it turn NC1 circuits into unintelligible branching programs? And the answer is generally no. Barrington theorem turns different but functionally equivalent circuits into different branching programs. And in the remainder of this lecture, we will only consider the problem of obfuscation giving oblivious branching programs of the same length. And recall, we say a branching program is oblivious if the sequence in which it reads the inputs does not depend on the branching program itself, but only on the input length. Right? So obliviousness is not a property of a single branching program, but always of an entire family of branching programs. Okay, but just really quickly to see that this is actually the case, let's maybe look at a quick example of branching programs that belong to two functionally equivalent circuits, but which turn out to be different. So let's say our let's take a single bit input program, and P1 of X is just, let's say, X and not X, right? How does Barrington's theorem proceed? Well, the heavy part, as we might recall from last time, is the AND gate. So we let's first look at the components of this branching program. How would we do a branching program just for the identity, or the branching program that just returns X? Well, branching program for this can be identity. So if x1 is if X is 0, it just returns identity, and if X equals 1, it returns such a cycle permutation sigma. Okay, that's a branching program that computes X. Now let's look at one that computes not X. Well, there I just do the reverse, right? If X, let's maybe draw that somewhere else. Now, with a little bit more distance. So not X. For the case that X equals 0, I return sigma, cycle permutation, which encodes 1. If X is 1, I just return the identity, which encodes 0. Okay, so for recall that in Barrington theorem, we had this business with conjugating these cycle permutations so that their product would result in a certain cycle permutation. So recall from these facts 1 and 2. Fact 1, 2. So we have cycle permutations. Let's call them tau 1 and tau 2. Tau 1, tau 2, such that, well, tau 1, tau 2, tau 1 inverse, tau 2 inverse equals our sigma. And we also saw, or I provided it as a fact, that we can turn any cycle permutation into another cycle permutation by a simple conjugation. So by a simple conjugation, I can turn this one here into identity and, let's say, tau 1, and that one here into identity and, let's say, tau 2. Okay, so now I have X and not X, and via Barrington's theorem, how does now the branching program that computes P1 look like? Well, here we have now, let's say here, the branching program that computes X. This is just it, tau 1, times or concatenated with the branching program that computes not X, which is, sorry, here I, of course, did anyone notice that I have a typo here? This should, of course, be tau 2, an identity down here. So tau 2, identity, and now just the inverse matrices. So inverse of identity is identity, and inverse of tau 1 is just tau 1 inverse. And here we have tau2 inverse, and here we have identity. Great. So Barrington's theorem turns us this program into this branching program, or this circuit into this branching program. And let's just recall that we just have a single input bit x. So here x, 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 x. Let's just check really quickly if this branching program really computes the correct output, right? What if x equals 0? Well, then we just take this one, multiply it with this one, multiply it with this one, and multiply it with this one, right? So x picks always picks the upper matrix in all these columns. We multiply them all together. So this is identity times tau2 times identity times tau2 inverse. That is identity. Okay, and on the other hand, let's say x equals 1. So then we multiply these guys here together. We always select the under one, right? X always selects the lower matrix here, and this is tau1 times identity, still tau1 times tau1 inverse. That's identity times identity is again identity. All right, and that's not a surprise, because this program up there, x and not x, well, one of them, x or not x, is always 0. So this is in fact the all 0 program. And now if we look into a second circuit, which really always outputs 0, and we turn this into a branching program of length 4, then again using Barrington, this results in identity, 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 and identity. And obviously, those two branching programs are not equal. So they're functionally equivalent, but they are not the same. So here we have an example of two different circuits that are mapped into easily distinguishable branching programs by Barrington theorem. So Barrington theorem really doesn't give us obfuscation, at least not an indistinguishability obfuscator, maybe some other kind of obfuscation, but it's unclear what guarantee this might give us. Okay, this would conclude my example on Barrington theorem. Is there maybe a question regarding this? Do we have any questions? All right, if not, then let's just continue with the actual subject matter of today, namely how we can use branching programs and multilinear maps to construct indistinguishability obfuscators. So the first heuristic construction without any kind of proof. So this was just, here I have multilinear maps, I'm putting things together. This I assume, or I hypothesize, that this is a good indistinguishability obfuscator, came in this paper. So this was basically a heuristic construction. So really, they put something together, they couldn't break it. That's typically not the best way of approaching cryptographic design, but in that case, it was kind of warranted because we didn't have any constructions of general purpose indistinguishability obfuscators before this work. So they had an idea, a reasonable idea from constructing an indistinguishability obfuscator using for branching programs using multilinear maps, but they couldn't prove a lot, right? They couldn't really prove anything there. And then in a later work, so this was 2013, this was 2014, or it was published 2014. Here, this they took essentially the same construction. They modified a few details, let's say slightly modified. And they actually could now provide this construction with a security proof. However, not with a standard security proof, but a proof in an idealized model. And when I say idealized model, you should think of something like the random oracle model. So the actual idealized model that's being used here is the so-called ideal multilinear map model, where the multilinear group itself is only accessible via some kind of an oracle. So in order to perform group operations, you need to use this oracle. Pretty much like in the random oracle model, in order to compute hashes, you need to query this hash oracle, right? This oracle of a random function. So this is not really the most desirable situation, that you need to resort to such an idealized model, but a proof in such a model is evidence that any attack needs to do something really interesting that is not captured by this idealized model. Right, so in a way, a proof in such an idealized model is something meaningful. But there is another drawback of the proof, of this proof, namely in what this security proof actually proves, which I will get into in the end of today's lecture. Maybe due to my technical problems earlier, we will only be able to go into that next time. Okay, but now we have seen Barrington theorem and branching programs, and how we turn circuits into branching programs, and that this transformation doesn't really hide a lot yet. So let's see, what if we're given branching programs and we want to obfuscate them? What are the challenges now? So the first challenge in obfuscating branching programs are so-called partial evaluation attacks. So if you give me two branching programs, P1 and P2, an adversary may actually look into the result of an intermediate evaluation. So it might just take this branching program, evaluate it up to some point, right? So let's say we know that these branching programs, say, come out of Barrington theorem, so we know what structure they have. And now we just evaluate them up to some specific point. So intuitively, an obfuscator, particularly an indistinguishability obfuscator, should hide intermediate results. If from an obfuscated program you can kind of recover intermediate evaluation results, this typically leaks something about the obfuscated circuit. So that's not good. So when we want to obfuscate branching programs, we have to design a mechanism which hides all partial function results or all intermediate evaluation results that are not yet the final results. So we want to leak, or we want to release the final result of the obfuscation because the function, because the obfuscator has to be correct. But we need to hide all intermediate evaluation results. So that's a first challenge that branching programs actually might give off a lot of intermediate results. And the second challenge or issue is maybe slightly more subtle. So when you give me a branching program, right? Let's say I have S10, S11, S20, S21, and S30, S31. It might be that the branching program says that, okay, so here you're supposed to use the first input bit, X1. Here you're supposed to use the second one, X2, and here X1 again. So in the first column, it's X1, second column, X2, third column, X1 again. That's what this, recall, that's what this input imp-I function dictated. It maps sort of an index in the branching program, an index of a column to an input bit, right? And the actual power of branching programs actually comes from the fact that they correlate these indices with certain input bits. So the power really comes from reusing input bits at specific locations again. Otherwise, these branching programs couldn't do more than finite automata. So it's really an important thing that if the branching program says, please use input X1 here and here, that you actually do use input X1 in both places, right? And now, of course, an adversary could go ahead and just not obey this rule, right? Instead of computing, let's say, a product like this, he might just go ahead and, let's say, here he chooses X1 equals 0, then he multiplies with that, and back here, instead of using X1 equals 0 again, he just chooses it to be 1, right? So he evaluates this program, this branching program, in a way which would never happen in an honest evaluation. So these are the two main challenges in sort of obfuscating branching programs. There are a few smaller issues which I will some of them I will mention at some points, but we will mostly look into how multilinear maps, and in particular leveled multilinear maps, can help us addressing these two challenges, or as a matter of fact, prevent these two types of attacks. So of course, for any given multilinear map, there might be other attacks, right? And what I'm going to show you is just a security proof in an idealized model. However, if the multilinear map is just used as it is prescribed by this ideal model, those two will essentially be the only attacks. Right? That's what these idealized models kind of help us to do. They help us to restrict the class of possible attacks to really some tiny, in this case, set of 2 attacks, and our construction will then have to address these challenges or attacks, and once they're ruled out, we can typically prove these constructions secure. Okay, good. So first, let's look into our challenge number 1. So the first idea on how to prevent an adversary from doing these partial evaluations is to just take the branching program and encode it in the multilinear group. However, giving this a moment's thought, this still, or let's say, if we encode it in the multilinear group, it will still allow us to multiply matrices. So we will still preserve correctness, but it kind of should prohibit all other operations on these matrices, in particular linear algebra, right? So if you give me, say, here these, I'm not going to give them names for now. If you give me these matrices here, and I encode them in my multilinear group with a suitable level structure, I will still be able to multiply these matrices due to the multilinear structure. I can still multiply them together, but I won't be able to look into these matrices. So I can do, let's say, polynomial computations on these matrices, that is adding and multiplying them, or adding at the same level and multiplying in matching levels. But I cannot kind of look into this. So if I cannot look into these matrices, I cannot just peek into them, right? That's prevented by the multilinear group. I cannot just perform Gaussian elimination, right? Because in order to do Gaussian elimination, I need to really look at the values that I'm working with and perform linear operations depending on what's there in this matrix. So at a first glance, it kind of seems that encoding this branching program in a multilinear map, 1, preserves functionality, and 2, prevents the adversary from looking into this branching program. So the first attempt would just be to take these matrices and at index, let's say it's index I, right? Here we have index I is 1, 2, 3. We encode these matrices at level I. For instance, at level 1 or in the first column, I will encode these 2 matrices at level 1. In particular, this will prevent that I can multiply those 2 together, right? If they're encoded at the same level, they cannot be multiplied together. Recall that I can only multiply 2 elements or matrices in a multilinear group if they are at levels that are compatible with one another. And compatible meant that taking and intersecting them will result in will result in the empty set. Okay, good. Thus, all that can now be computed are products of the form Si xi prime I for when we go over such sets over such subsets J in our universe L, right? L, that's just the universe for now. Okay, and really the nice thing is that which is already enforced by this is that every I can only appear once in this product, right? So every index, every column, from every column we can use at most one element. All right, good. However, this still allows us to perform partial evaluation attacks, right? In particular, if we think about it, then this multilinear group, what does it even hide? If we start with a fixed branching program, then, if we start with a fixed circuit, then this, by Barrington theorem, results in a fixed branching program. But if we now just encode this in a group, I'm not using any randomization here. The group doesn't have any chance of hiding anything. Because think about the discrete logarithm problem when I'm not using a random element. If you go into any D-log hard group and I'm gonna give you g to the 7, and you know specifically that this is a g to the 7 because 7 was now just a constant, then you can easily check that this is the case by just computing g to the 7. So you can actually check whether I gave you the correct element. So whenever we do these sorts of things, we need to inject randomness at some point. And here we haven't injected any randomness yet. We have just encoded things in the branching program in the group. Great, this preserves functionality, but somewhere some kind of randomization needs to come from. And all right. Say you have two branching programs, P1 and P2. They are functionally equivalent. And as it just so happens, their first part, let's say, and we can, from these examples we had earlier, you can easily construct something like this. The first part is identical for these two branching programs. And then in the second part, they do something else, right? Then this guy does something. They're still functionally equivalent, but they do something else here. And a simple way of constructing an example like that would be just to choose these guys to be all the identity matrix, right? I'm constructing branching programs like this. Then if those guys back here are functionally equivalent, then the extended branching programs are still functionally equivalent. But now what I can do is I can actually still test if these branching programs are of this form. So I can still compute partial evaluations in front here and see if this branching program is actually of this form. Just noticing that for an actual attack, this in order to distinguish this, these guys should do, let's say, something different. Let's say this guy does something else here, right? But now let's assume they're still functionally equivalent. What an adversary can do now is go ahead and compute a partial evaluation. Compute partial evaluation here. Compute partial eval here, and check if output is it, and check if out, oh my god, that's not a good color. Put is it. I'm running out of colors here. This could, computing such a partial evaluation can now still allow us to distinguish these two branching programs from one another, right? So we have to have a mechanism that penalizes these partial evaluations. And this is possible even if you're using, let's say, if the input map says to use x1, x2, x3, even if you do the evaluation correctly with respect to the input map. Okay, good. So we need a mechanism which penalizes and in the ideal model, in fact, prevents these partial evaluation attacks. And this is an idea which for branching programs has been around long or has been predating these works on obfuscation by roughly 25 years. So these are ideas that are back from the late 1980s, in particular due to a work of Joe Kilian from 1988. So branching programs, or it was long known that branching programs are really useful for doing crypto. They're a model of computation that's really nicely, that fits nicely with crypto, because they allow for easy and very simple randomization. This was noticed back by Kilian. So the idea is now roughly as follows. Given a branching program, we choose random invertible matrices R0 until RL. So we choose as many as we have as the branching program is long, +1, and random so-called bookend vectors S and T, and we set first some utility to be utility transpose is U transpose times R0. Next we set, I'm gonna draw this in a second, so let me maybe just, so let's say we have our branching program here. Let's make it a little bit bigger. You see, I'm gonna need some space here. So I'm gonna do two things. The first thing is I'm gonna just take all of these matrices SIB, and I'm gonna let's see, this is S10, S11, S20, S21, S30, S31. And what I'm gonna do is I'm gonna conjugate them with these random matrices. So S10 is turned into this S tilde 1, 0, which I just get by multiplying it with R0 inverse from the left side and R1 from the right side. And down here, the same. Multiply with R0 inverse and R1 from there. Next thing, I'm gonna multiply here with R1 inverse and here with also with R1 inverse. Here I'm gonna multiply with R2 and here as well with R2. And the same procedure here, R2 inverse, R2 inverse, and here with R3. R3. Okay, good. So this is this middle step of this randomization procedure. And the first thing we notice is that once we multiply things together, right? If you multiply, let's say, this guy with that guy, there's a 2 missing here, with that guy and that with that guy. Actually, this R1 here and this R1 inverse, in fact, cancels out, right? This R2 and this R2 inverse, they cancel out. So this randomization, in some sense, makes these matrices SIB tilde random. It injects randomness into them, but it still preserves the correctness of evaluation. So when I do my evaluation, I will still get the correct outputs, except for, of course, these things in front here, this R0 inverse and for that, and this R3, and of that, so to speak, I'm taking care of with these bookends. So by the way, the bookend vectors should not be S and T, but U and V, U comma V. So these vectors, here I'm having my U and there I'm having my V for lack of space. This U is just multiplied with R0 and this V with R3 inverse here. And we see that when we evaluate this, it's bad that these tildes are floating so much over these S's, U's, and V's, but nevertheless, we see that these random for correct evaluations, these randomization factors all cancel out. So we still have the U and V here, right? But we know that this branching program here should either return, let's say, the identity or some cycle permutation sigma. And now we can just for random u and v identity and or inner product of u and v, u transpose v we will have here, and u transpose sigma v, they will be different, and that's all we need. We will need in order to ensure correctness, right? So if the branching program evaluates to 0, that is identity, then we will just get the inner product of u and v. If not, if it evaluates to 1, we will get something that's different from this inner product of u and v. Okay, however, the nice thing now that this randomization guarantees us is that if we compute a partial evaluation, that is without going front to back, without computing the program completely, then in these partial evaluations, let me take a different color.
Maybe I'm mistaken, but aren't there other things that can come out of this branching program other than the sigma? Didn't we have it that everything that's not the identity can basically be an output?
But you can, I don't know how explicitly I said that, but you can always turn your branching program via this conjugation trick into a form that if it outputs 0, if the output is 0, there will be the identity matrix. If it outputs something non-zero, it will always be this fixed, some fixed cycle permutation sigma. So you can always achieve this via this conjugation trick. So I didn't go too deeply into this detail, but you can assume that if the output is 1, you will have this permutation, the cycle permutation sigma. I mean, maybe let's see. I guess we won't have time for that. I can maybe let me add that or note that down somewhere. Maybe link to material about branching programs and their normal forms. Okay, good. But the important thing of this branching program randomization here now is in partial evaluations, some Ri or Ri inverse will not cancel out. And that implies that this result of a partial evaluation is uniformly random.
Sorry, I have one question here.
Yeah.
Because I understood the partial evaluation before such that, for example, you change the value of x in between.
Oh, no, sorry. That's challenge 2. So
okay.
Challenge 1 is you don't you evaluate it somehow on a subset, right? Let's yeah. Did I do that here? Yeah, sorry, no.
Oh, yeah. So these are the in-between results then. Is that right?
Exactly.
Oh, okay.
Exactly. So, I mean, I had that in a few slides earlier. So this, the challenge one are these partial evaluations and intermediate results. This is about learning intermediate results. The second challenge is changing the input bit in a way that's not allowed by the branching program. That's the second challenge, right?
Okay.
I don't know if we're, maybe we're gonna get there despite all my blunders today. But what this guarantees is, or what this helps us to achieve, is that if you don't fully evaluate the branching program, you're sort of left with either some Ri or some Ri inverse, which is not partnered which is, with its inverse, which will not cancel out. Good. So, good. Partial evaluations are uniformly random. Okay, there's a second thing that's necessary, or a second aspect to this branching program or randomization, which is maybe not directly linked to these partial evaluation attacks, but more this is more a gadget that's introduced into this construction in order to enable proving its security in this idealized model. So for proof reasons, there will be additional randomization factors alpha I, B, right? And we will set if we look at this, this alpha I, B is, this depends on B, but here these guys, we've seen they do not depend on B, don't depend on B. Okay, so in a way, we're having now this random scalar factor alpha IB, which maybe I should say here, of course, shouldn't be 0. So we have these matrices. I mean, SIB tilde as before, but now we're still multiplying them with a uniformly random scalar. In a way, these alpha IBs are there to sort of inject additional randomness to use the security of the multilinear map. So both the R's and the alphas are used as randomizers for this multilinear map. And now, of course, I wrote over. Okay, let me maybe, I think for that I can have time. Here, this depends on B, and these two, they don't depend on B. If we now evaluate, so we don't change these U tilde and V tilde, and if we now evaluate our branching program, here this doesn't need to be X in, this can be any Xi prime. Then if we evaluate this, we will have, this is the, let's say, evaluation as before. Evaluation as before. But since these alphas are just scalars, we can pull them all out. right? We will get this additional per input randomization factor, right? Here, I mean, what I've done here can be pulled out. Be pulled out of the matrix product. Okay, good. So this is that. So it, in a way, doesn't really influence the matrix product, since it's just scalar factors. We have this subset product which just floats in front of this matrix product. Okay. And now, with these ideas all together, we can construct ourselves a preliminary obfuscator which prevents these partial evaluation attacks, but does not yet prevent the input mixing attacks. And the idea is as follows. So you give me a branching program. So from now on, really branching programs are the level or the model of computation we work on. We don't, this branching program should be an oblivious branching program, can come out of Barrington theorem or not, but the programs we obfuscate are branching programs. So the input to our obfuscator are branching programs. So given such a program, how do we obfuscate it or do this preliminary obfuscation? For this slide, since it's just the preliminary obfuscator, I'm just leaving away the levels of the multilinear map, right? I've talked about the levels a bit earlier, but we're going into this in the second part when we, or in the second challenge. So we take these SIB tilde that we've just defined here. So using all these randomizations, the alpha IB and the RI-1 inverse and RI, this is my SIB tilde. I just sent this into the multilinear map, right? I encode this, or in the multilinear group, I encode this in my multilinear group. I'm not talking about the levels yet. And I'm going to do the same just with the alpha IB, right? So maybe let's, just as a slight note, let's recall that SIB is alpha IB times SI inverse RI, sorry. RI inverse SIB times RI. Here we have the alpha IB. We also encode them in the multilinear group. And now I'm giving you three things. I'm giving you this U tilde encoded in the multilinear group V tilde and the product of U or the inner product of U and V. So that's what my obfuscated program consists of. These, now I'm of course going through all IB here. Here I'm also going through all IBs. That's how my obfuscated branching program looks. And we've seen kind of a high-level idea why this should prevent an adversary from running these partial evaluation attacks, right? If you give me these on the one hand side, since they're encoded in the multilinear group and they're randomized mostly via the alphas, the adversary cannot do linear algebra. So from this description, he cannot recover these RIs or RI inverses or whatever. And on the other hand, if he does just a partial evaluation, some Ri will still float around and completely hide what this partial result is. So how can I evaluate such a preliminarily obfuscated program? Well, you give me an input x, and now here this should be x imp I, and we just multiply all the stili I comma x imp I together, multiply the left book and u on the left, the right book and v on the right, and then we just test whether this is the same as uv, this inner product that's already given up there, times this per input randomization factor, which we can recompute from this thing here, right? If this check passes, we are sure that the output of our branching program is 1. If so, output is 0. I mean, the identity matrix encodes 0. Otherwise 1. Okay, so this is about I mean, from this we can see that this obfuscator is correct. Basically, really, the main idea that goes into this is that or why correctness is preserved is 1, these randomization factors here cancel out as we've seen before in a correct evaluation, and second, we can sort of pull out this product of the alphas, and now since we're being given all the alphas, we can just recompute them and test for equality in the end. Okay. This is the preliminary obfuscator, which in fact provably already prevents these partial evaluation attacks, but it doesn't have any safeguard, as you can see yet, against these input mixing attacks, right? So here you're supposed to choose x imp I, so you're supposed to choose the bit b that's dictated by imp I, but there's no mechanism yet that forces you to actually choose it that way. You could choose any bit still. Good. Are there any questions so far regarding this? All right, then let's, okay, well, great. Now I can erase this again. Okay, good. Now let's turn to challenge number 2, input mixing attacks. So we still have to deploy some form of countermeasure against these input mixing attacks. Since recall that our adversary or the malicious evaluator can just compute with let's say xi, with some xi which is different from x imp I, right? We recall that the power of the branching programs comes from the fact that that we do choose that this imp I function is, say, not trivial, that we use the same input bits in very different locations. And now we need to force the evaluator or adversary to actually choose this x xi prime as x imp I. And what we're gonna utilize for that will be the multilinear or the level structure of our multilinear map. This brings us to this concept, so-called straddling sets. They were called straddling sets in this paper, in the second paper by Barak et al. And multilinear jigsaw puzzles in this original GGH RSW paper. Yeah, we will use the level structure of the multilinear map. So what we're going to do is, instead of encoding, in fact, we're encoding not the SI, but the SI tilde, instead of just naively encoding them at a level which consists of this singleton set I, we will use a slightly more sophisticated level structure. This level structure will enforce that the evaluator has to commit to an input xi prime when it chooses the matrix S I comma or S tilde I comma xi prime. So once you've chosen one matrix of this form, this level structure will force you to for all other inputs j for which it holds imp j is the same as imp I, you will have to choose x prime j as x prime I. So whenever imp I equals imp j, you have to provide the same input, or the multilinear map will not let, or the level structure will forbid you to do evaluation. Right? Let's see how we can do this. So in the really simple example above, we had that this, again, tilde here, SI0 was encoded at level I, and SI1 was also at level I. What we're going to do now is we're going to make them different. Okay. Yeah. Good. And for that, we'll look at these jigsaw puzzles. So we first recall that the multilinear level structure of our multilinear map enforces that two encodings, x at level I and y at level j, can be multiplied if and only if I intersect j is the empty set, if I and j are disjoint. And this results in x times y at the level I union j. We will assume in the following that the input, and in fact each input xt is used k times in the branching program. So there are exactly k indices I with imp I equals not t int, yes, int I equals t, not xt, but t. And in fact, we've seen this idea of oblivious branching programs, which in fact, given any branching program, results in a branching program that has this property that every input is used the same number of times. So this is not a severe requirement here. And now for the moment, or for an example, let's assume we only had a single input x1. Of course, this results in trivial programs, but this is just to illustrate this idea of jigsaw puzzles. We assume there was only a single input bit. And then, of course, we'll look into how this can be generalized to arbitrary branching programs. So let's go to our warm up with only one input bit. Now the idea is as follows. So let's say we had a branching program S10, S11, S20, S21, S30, S31, and S40, S41. So for now, in kind of so my indices I are 1, 2, 3, 4. But now I'm also gonna write down the universe U up here. So what I'm gonna do is I'm gonna associate these locations here with 1 and 2, this with 3 and 4, 5 and 6, and here I only need maybe I should use a different color. Actually, here I did use a different color. Okay. So let's use maybe orange. So here, we have 1, 2, 3, 4, 5, 6, and 7. Okay. So what I am going to do is this S10, I will encode at a level which just consists of, sorry, no, now it's wrong. I should have a little bit more space here. It's a bit too tight. S10, S20. So I'm gonna encode this S10 at the level 1, 2. Right? I'm gonna write it like this. When I attach a little box, this means this is at level corresponding to the set 1, 2. And this S11, I'm just encoding at the level which consists of the singles in set 1, right? So now I have them encoded, in fact, at different levels. And now I'm gonna continue like this. So this guy here up here, I'm gonna have him encoded at level 3, 4. This one at 5, 6, and this one just at, well, 7. What am I gonna do with this guy here? Well, in the end, everything has to match. So I'm gonna use 2, 3 here. Here I'm gonna use 4, 5. And here I'm gonna use 6, 7. And with this, we kind of see where the name jigsaw puzzles comes from, right? Let's say we have an adversary who wants to use 0 here, wants to use this matrix here, and now he tries to use that one with it, right? In the second step, he tries to change his mind. Actually, I don't want this input x to be 0. I want it to be 1. But now he has a problem, right? Because now these two level sets, they intersect. All of a sudden, we have 1, 2 intersect 2, 3 is the set 2, which is not the empty set. And that means S1 or the encoding of S1 0 at level 1, 2 cannot be multiplied with S2, 1, which is at level 2, 3. Right, and this is where this idea of jigsaw puzzles come from. Once I've chosen the first piece, which is in this case this 1, 2, this 2, 3 will not fit anymore. I cannot, no matter at which point I change my mind, I will have a mismatch. These puzzle pieces will overlap and not fit together anymore. If I now we've seen that I cannot change my mind at the second position. So at the second position, I have to choose the same thing. I have to choose S2, 0. Now, what if I try to change my mind in the third position? Then the same problem happens, right? Now, 3, 4 intersect 4, 5 is 4, which is not the empty set. And so changing our mind doesn't work. But on the other hand, if I don't change my mind, if I go through with the same choice, then we see that all these sets up here, all level sets up here are disjoint. And since they're disjoint, I can multiply these matrices together. Okay, I think I'm almost done. Basically, the rest will take 5 minutes. I'm gonna postpone it until next time. Are there
just a quick question?
Yes.
So what happens if you, in this example, choose bot, and for the last two, the upper ones, then the sets are disjoint, but you're missing the 4. Would that not work?
You're missing one of the matrices.
No, so in this case, if you choose S11, S21, S30, and S40.
Okay, one second. Let me make it in some color. So you're choosing the lower one. You're choosing
for the first two the lower ones, and for the last two the upper ones. Yes.
For the last two, the upper ones. Let's.
Then the level sets are still disjoint, but you would be missing the.
Yes. You're missing. Good. There. Let me think. What happens here now? So the problem with that, I mean, you're having a hole in there. That's the first thing. But I mean, in the full construction, for that I have to go a bit back. Let me go to no. let me go back here. When you have a hole in there, when you go to this check here, right? On that side, you will not have a hole in there. So on that side, you cannot have the hole. On the left side, you do have the hole. So that case will again be taken care of by this per input randomization term.
Okay. Yeah, that's
so yeah, it's that's a subtle thing, but maybe there let's just say very high level. If you have a hole, you will not manage to have this hole on the other side. So you run into a problem.
All right, thanks.
Awesome, thanks. Okay, are there more questions? Okay, then thanks a lot, everyone. I hope to see you again next week. Thanks a lot. Until then.